All right. All right, so let's get started. All right, so we actually we've been talking about elements, compounds. We learn how to name them, right? And then now we are going to actually learn about how we can actually do reactions with them. That's what we're going to do in this chapter. And we're going to learn about how to balance the chemical reactions. And we're going to also learn about different type of chemical reactions. Okay. And so let me jump to my PowerPoint. Okay, there I go. Okay. So as we've said in the law of conversation, right? Like we cannot actually, right, lose elements, or like if we have, if you look at the simple reaction that we have here, H2O, right? If you have two hydrogen, right, and we have a subscript here, if you have two hydrogen reacting with the oxygen, and if we have two hydrogen here, that's balanced. But if you look at the oxygen, we have two oxygens, but we have only one oxygen, right? So we need to actually have, same number of elements on the product side and same number of elements on the reactant side. Okay. And the reason that that reaction has to be balanced is, again, it's going to be against the law of not conversation. I keep saying conversation, conservation, right? The conservation of the elements. So if you have same number of elements in the product, you need to have same number of elements on the reactant. And how we actually balance them, right? You just balance them by playing. Okay, this is important. You cannot play with the subscripts, right? Because this is actually how the elements is composed, right? Oxygen, when we say oxygen, it's O2. It's diatomic, right? We learn about this. And so the only thing that you can do is you can actually play around by putting these coefficients in front of the elements and compounds, okay? So by placing this number, whenever you place 2, for instance, this is going to be multiplied by these 2, and now you have 4 hydrogen. And if you look at here, same thing, right? You have 2 here and 2 hydrogen here, so it's going to be 4 hydrogen here too. So as you can see, the number of hydrogen, the moles, is equal right now, 4 hydrogen and 4 hydrogen. And if you come to oxygen, it's the same thing, right? So we have 2 of them here, 2 oxygen. And now over here, if you look at it, now there's a coefficient here. And since you have 2 of them, you have 2 oxygen there too. So now, as you can see, it's balanced. And so you might be asking, like, how we're going to do it? Well, it's just a try and error, basically. Okay, try and error. You're just going to put a number, try to make it balanced. Just keep continue, okay? Let's do some example. So the example is, again, here, right? If you look at the mercury is, and again, there is no way, it's not just like a one way of balancing, okay? There's going to be many different ways of balancing in terms of the coefficient. Let me actually write this reaction over here so we can look at it. You don't see my white screen, right? Do you see it?
No.
Yeah, I'll just share it all. Okay, let me just share my screen instead. Stop share. Everybody's doing fine, right? Nobody's sleeping. All right. All right. So now again, this is unbalanced reaction, and again, it's just a try and error, right? You're just going to look at it, and you're going to try to work your math around. So you have one mercury here, one mercury here, and if you look at it, oxygen, now we have one oxygen here, and we have two oxygen, right? So we need to somehow make this oxygen either two, right? So that it's going to be balanced, or you need to make this oxygen one, right? So that it's going to be balanced. So, you know, if I were, you know, if I want to balance this, I will just put like 1.5 here, right? If you put 1.5 in front of the oxygen, because 1.5 times 2 is 1, right? That's like one way of balancing, right? But you can actually, if you don't want to work with the fractions, well, you can actually put 2 here, right? Because you have 2 oxygens here. How can you have 2 oxygens here? You need to put 2 here, right? So that you are balancing, right? But whenever you do that, now you have 2 oxygens, but all of a sudden you have 2 mercury here too, right? So the mercury is not balanced. So therefore you have to come here and also put 2 in front of mercury so that you're going to have 2 mercury on the product side. Okay? That's how it is really. Just try and error. All right. And we're gonna do some example. Actually, let me give you an example. Let's say we're gonna burn carbon, and again, this is, and let's say we're gonna burn methane or propane. This is very precious right now, right? In Texas, everybody's trying to buy propane, and whenever you burn, this is a fossil-based again, you know, fuel, you're gonna produce carbon dioxide, right, and water. And let's try to balance this reaction out. Is this balanced? Probably not, right? Let's see if we can balance it. So how many carbon do you have here on the product, on the reactant side?
3.
3, right? So over here, when you come here, you need to also have 3 carbon. And how many carbon do you have here now? Only 1, right? So what do I need to do? I cannot put, like, again, I seen students actually doing this, right? In order to balance, they come here and they put 3 here, okay? That will be wrong, because like whatever you are doing right now is you are changing the composition of the material, right? So you are playing with the chemical properties, okay? You are creating a new molecule actually. I'm not sure you are going to get a Nobel Prize for this, but you know, you're making a very new molecule, okay? So you cannot do that. So the only thing that you can do is you can just put a coefficient. You can just change the coefficient here. So now if I put 3 here, now I have 3 carbon here, right? So the carbon is taken care of. Make sense? And now I can come to oxygen now. And so over here I have, let's pick a blue color, 2 oxygens, right? Or maybe I can look at the hydrogen first. Or it doesn't really matter. You know, which one you pick doesn't really matter. Let's go with the oxygen. So you have 2 oxygens here, right? And if you look at it here, you have 3 times 2 is 6 oxygen, right? And then if you come over here, you have actually 1 oxygen, right? So as you can see, it's kind of like uneven, right? This is an odd number. 6 plus 1 is 7, right? 7 oxygen, and you have 2 oxygen. So as you can see, it's kind of like one of them is even, one of them is odd. So let's leave the oxygen for now, and let's look at the hydrogen. Let's balance the hydrogen first. And if I pick another color, so we have 8 hydrogen here, and over here we have only 2, right? What do I need to do? I need to play with the coefficient, right? Which number should I put?
4.
1, 2, 3, 4, right? Good. Because 4 times 2 is 8. Now the hydrogen is taken care of, correct? And now I need to go back to my oxygen again, because I just changed the oxygen number. So I have 4 oxygen now, right? Because 4 times 1 is 4. So oxygen is 4, and 6 plus 10, 6 plus 4 is 10 oxygen. Let's say oxygen, because it looks like 0, right? And so you have 10 oxygen here and only 2 here. So I need to change the coefficient again. What number should I put here?
5.
5, right? Okay, very good. Everybody see that, right?
Yeah.
Okay. So again, it's not that difficult really. You just have to kind of like play around, right? Makes sense, right?
Yeah, it does.
Any questions? All right. So again, these are chemical, balancing chemical equations, and we're not going to do anything else. We're just going to balance it, okay? We're not going to learn how they are reacting. I'm not going to be like asking if you have 10 grams of this, how much we're going to be producing. We're not going to do all that, okay? And then I just want to briefly talk about the type of reactions. And the first one is, again, these are just definitions, okay? And and some of them are obvious, like this one, like whenever we say combination reactions, obviously, whenever you're like making a cake, right? You mix 2 things up and then you make cake, just like that, right? You are mixing A and B, and then you are making AB, right? So the simplest example is like H2 plus O2 making water, right? This is a combination reaction, okay? Or you mix up hydrogen with chlorine, and then you get hydrogen chloride, okay? Combination. Nothing so fancy about it. And if you have the opposite of the combination, then you have a decomposition, right? Decomposition means that, you are kind of like, getting the more the substance, right? Like you have a compound, let's say you have mercury oxide, and if you heat this up, now you are getting these elements. We're separating the elements, okay? And so you have mercury and you have oxygen. Make sense? Okay, so again, this is decomposition. And then we have single replacement reaction, okay? And in the single replacement reaction is, why we are called this single replacement? Because if you have like this guy, metal, zinc, what it's doing is, it's just kind of like kicking these hydrogens out, right? It's just kicking the hydrogen out and replacing with hydrogen by itself, right? That's why it's called replacement. And the best example is, again, whenever you have a metal, right, such as zinc, if you react with HCl, hydrogen chloric acid, hydrogen chloride, you're going to release hydrogen gas. And again, the hydrogen gas is flammable. This is what they do in the high school. I'm sure maybe your teacher did it, right? You can actually get an explosion by flaming. By if you have like a fire, the hydrogen gas is going to explode. It's a flammable gas. So this is single replacement reaction. I think I missed the P here, replacement. And then we are going to have a double replacement. And double replacement is, again, you're just like, you're replacing both of them, right? So we are not like, we are kind of like exchanging the cations and anions, okay? Because we know that, right, from the previous example, previous lecture, right? If you have a K is potassium, and that's actually plus, right? And then we have chlorine, which is negative, kind of like sodium chloride, the example that I gave you all the time. And then you have this guy here, which is silver nitrate, and we know that silver is metal, so silver is plus sign, and then you have nitrate, right? NO3. Okay, maybe I can write the anions blue so that it's gonna make more sense. Okay, so again, if you look at these reactions, right, these are again, we have, in some reactions, we have this term. Do you know what this means? Aqueous? Aqueous. Aqueous. This is solid. What's aqueous means?
Liquid, water.
Right? Aqueous means it's like water. And this means that this potassium chloride, aqueous means like whenever you have like sodium chloride, for instance, right? Sodium chloride, whenever I have the sodium chloride right on my table, if I add this in water, the sodium chloride is gonna dissolve right away, okay? And so whenever it dissolves, you're gonna again create these anions and cations, right? If you have a positive charge, this is a cation, right? The positive charge are cation, and negative charges anions, right? Anions. These are anions. That's why we call this aqueous, because the sodium chloride is going to exist as sodium plus and chlorine negative in solution. Okay, and so in the double replacement reaction, what we are doing is we are just replacing the cations with the anions, right? So that's what it is. So here now potassium was the cation, right? And I mean here the silver was a cation with the silver nitrate. All you have to do is just we are just switching, right? So you're just writing potassium, and now it's actually reacting with the nitrate. Now you have potassium nitrate. You see that, right? You're just switching around. That's what it is. And then you're getting other product, which is silver, and silver is mixing up with the chlorine. Make sense? This is what it is, really. Okay. Any question with this, everyone? Good.
Good.
And as you can see, if the salt here, like again, this is a salt, and this is a salt too, right? Salt is, again, it's not just like we in chemistry we call them salt. Whenever you have a metal, and if you have like chlorine, it's going to be a salt. Okay, but here, as you can see, this is solid, and that's why this is not going to dissolve, and you're going to see a precipitate in solution. You're going to see something falling out of the solution on the bottom. That's what it is. If it's dissolved, then it's going to be always aqueous. Okay, and final reaction, I just want to show you, this is actually oxidation and reduction reactions. And let me just write this down. Let's clear this canvas for now. Okay, so now we have iron. Let's actually, let's balance this reaction first. I think that's a good exercise. F2, what is it? FTO2, right? Okay. All right, so let's get rid of this thing. All right, so here is our reaction. Everybody can see it, right?
Yes.
All right, and it's not balanced, right? Let's try to balance it.
Okay, I got it.
Again, you know, there's not like one way, but you may want to like put 2 here, right? But then you're going to have oxygen unbalanced. So I think the easiest way is like to balance the oxygen first. So let's put 3 here, 2 here. And if you put 2 times 3 is 6 oxygen.
Mm-hmm.
In order to have 6 oxygen, what should I put? 3, right?
Wait.
And if you look at it here, how many iron do we have? We have 4 iron, and I need to put 4 here, right?
Mm-hmm.
Okay, very good. Okay, so now this is balanced. This is taking care of it. Okay, so why we are calling this oxidation and reduction reaction is, okay, so now here's the exciting part comes in. So again, when we say, whenever the elements are neutral, right, we say that the charge was what? The charge of the element, whenever they are neutral, they are not reacting.
Negative?
0.
Negative?
They're not
What is it?
reacting.
What is it?
Balance, 0.
No
0,
charge.
right? 0, exactly. So if I ask, what's the charge of iron? What's the iron charge here?
0.
0. Everybody agree?
Mm-hmm.
Right? Because why? Iron didn't react with anything else, right? So iron is still having, whenever we have a reaction, remember I told you, it's all about the number of electrons, right? They actually exchange the number of electrons. And whenever you have a unbalanced electrons, right? Because the number of protons and electrons has to be the same. If it's not, then you're gonna have a charge, whether it's gonna be negative or plus, right? And oxygen is the same thing here, right? This is a diatomic molecule, and therefore oxygen right now is happy and it doesn't have any charge, 0 charge, right? So if I come back to here, now they reacted and there's an exchange between the electrons. And whenever you have an exchange, right, now one of them is going to gain electrons and one of them is going to lose electrons. Okay, let's look at the charge of iron and oxygen. What's the iron charge here? Or oxygen's charge here? Do you remember the previous chapter?
Yeah, it should be -2 oxygen.
Very good. Oxygen is -2. Everybody see that, right? Because you can do this in 2 ways. Either you can back crisscross this thing, right?
Yeah.
Right, like that. You can do that. Or if you know the oxygen is group 6 is always -2. That's what we learned from last chapter, right?
Yeah.
And so oxygen is -2, and that's going to leave you, right? If you don't want to do crisscrossing, then this side, oxygen is going to contribute 2 times -2 is -6. And in order to have a neutral compound, right, at the end of the reaction, we want to have a neutral compound. Iron has to be +6. So that when you add this up, you're going to have 0 charge. So therefore, iron has to be +3, right? Because 2 times 3 is 6.
Mm-hmm.
Makes sense, right?
Yeah, it does.
Okay, everybody? Okay, now we are back in the business. So now let's look at iron here, okay? So if you look at the iron right now, iron was 0, right, before the reaction, and it went up to +3, right?
Mm-hmm.
Okay, so if I ask you what happened to iron, did it gain electrons or lose electrons in this reaction?
Lose electrons.
Lose electrons. Very good. And why is that? Because again, if you don't get this right away, you can just give a imaginary number, right? Let's say iron was, it doesn't really matter, okay? We are just doing an example. Let's say it has 10 proton and 10 electron, right? So if I come here now, iron has, again, I cannot change the number of protons, right? It has to have 10 protons.
Mm-hmm.
And since it has +3 charge, do you think the number of electrons is going to be the same?
Mm.
No, right? It has to be lower than 10, right? Because proton is plus charge. So you have 10 protons. So you cannot have 10 electrons, otherwise iron is not going to have the +3 charges. So therefore you need to have 3 less, right? Make sense? Right?
Mm-hmm.
1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, right? So that because plus charges and negative charges are going to cancel out, and when you cancel them out, you're going to have, oops, I cancel them out. Yeah, I get excited, I guess. So you have, again, you have 3 charges here. You see that, right?
Yeah.
Okay, so therefore the electron must be 7 here. You see that, right? Again, if it doesn't make sense right away, you can just imaginary numbers, and it's gonna, it doesn't have to be the same numbers of the number of protons. As long as you give, you keep track of it, it should be fine. So as you see, it lose electrons, okay? So whenever you lose an electron in a reaction, we say that iron, sorry, this is actually, we said that iron is oxidized. Let's erase this. Oxidized. Okay. In chemical terms, we said that in this reaction, iron is oxidized. Okay. It loses electron. It means it's oxidized. Or you can call this oxidation. Let's call it oxidation too. Same thing, basically. Makes sense, right? All right, so let's go back and let's look at oxygen now. What happened to oxygen? Again, oxygen was actually 0, right? And then it went from 0 to
-2.
-2, right? So it seems oxygen did lose electron or gain electrons?
Gained.
Gained. Whatever iron let go, oxygen picked up.
Exactly, right? Just like the ionic reaction that I explained to you. Remember the sodium and chlorine? Sodium was giving away the electrons and the chlorine was accepting it. Why? Because oxygen is non-metal, and non-metals are electron poor. And if you are electron poor, you're in desperate of electrons, right? So therefore, oxygen here gain electrons.
Mm-hmm.
And whenever you gain electrons, in chemistry, we call this a reduction. And we call oxygen is reduced. Right? We say in this reaction, oxygen is reduced. Iron is oxidized and oxygen is reduced. And therefore, if you look at this reaction, we call this reaction an oxidation and reduction reaction. Okay? And there's one more thing that I want to mention here. And it's just a kind of like a flipping the world and kind of like a little trick, right? So if you look at the oxygen, right? So if you look at the oxygen caused iron to what? If oxygen wouldn't be present, right? Do you think the iron will be oxidized?
No.
No, right? So therefore, we call oxygen an oxidizing agent. Makes sense? It's kind of like you're reversing it. Even though oxygen is actually being reduced, right? Oxygen is being reduced. We call oxygen here in this reaction an oxidizing reagent. Make sense? Why? Because it caused the other party to oxidize. Make sense? If oxygen wouldn't be present, iron wouldn't be oxidized, basically. And same token, if you look at the iron, even though iron is oxidized, it caused oxygen to being reduced, right? So therefore, we're going to call the iron a reducing agent. Okay? We are kind of like calling the opposites. Make sense, everyone?
Yes.
Okay, cool. Any questions about this in general?
Okay.
All right, so let's do one example with oxidation. And then we can move on. Let's see.
Oh,
That was a big gasp.
Professor, we're gonna cover only chapter 7 today.
Yes. Chapter 7 is done actually. This is the last thing that I'm going to be talking about. So
Wow,
that's
that's
so bad.
great.
Yeah, chapter 7 is version. I'm planning to start chapter 9 actually, but I'm not going to finish it.
Quiz we're gonna have on chapter 7 and 9.
No, again, I'm not
Oh,
going to finish the chapter 9 probably, because chapter 9 is a little long.
Oh,
We
okay.
have a lab due this week, correct?
No,
No,
because
next
I
week.
need to finish the chapter 9 for the lab.
We have labs every 2 weeks, right?
Yeah, every 2 weeks, but sometime I'm going to play around because if the chapter is not done, because you don't know what we are going to do. Like if in the lab it's talking about acids and bases, and if you don't know what the acids and bases, right?
Mm-hmm.
So we
Okay,
just
so here's the reaction, and I'm just going to write it down as aluminum, and you're going to come up with the reaction plus oxygen gas and then you're producing aluminum oxide. You should be able to write the formulas of all of these right now. Okay, why don't you write the reaction down just like the way that we did on top. I'm just going to leave it there so that it can be, you can use it as a reference. And balance the reaction. Okay, write the reaction down, balance it, and find out which substance is being, let's say, like which one is being oxidized. Let's say the substance.
the substance being oxidized is.
Yeah.
Would that be aluminum?
Oxidized, and then let's write down also the other one. It's kind of like a stock market, right? If there's a substance being oxidized, there must be a substance being reduced. Okay, let's write it down. And then maybe we can do one or two.
The formula for aluminum oxide would be Al2O3. Right?
ALT.
No, Al2O3.
Yeah, I guess you're.
Yeah, that's what I got.
Yeah, he crisscrossed.
Messed it up. Okay. All right. Everyone?
Yes, that's what I got.
Everybody agree?
Yes.
We have a consensus. Okay, aluminum is aluminum, right? What about balancing? Did you balance it? Plus oxygen gas. What I'm gonna? Why should I put? Should I put O, or should I put O2?
O2. No,
O2,
no.
right? Again, this is. Huh?
Wait a minute.
Should I put O or O2?
O2.
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 Again, because you've never seen oxygen standing by itself, right? Because oxygen is diatomic. Okay. Make sense?
Mhm.
Okay, good. Because if you put O, it's going to mess up your balancing, right? And then whenever I come here again, this is my previous chapter. I know that aluminum is Al.
Mhm.
And what's the charge of aluminum?
+3.
+3, good. And oxide is, I know that oxide, I call oxygen as an oxide. So it must be oxygen. And what's the charge of oxygen?
Negative.
-2
Very
times.
good,
Yeah.
right? And if you do crisscrossing, then you're going to get Al2O3,
O3.
right?
Mhm.
Very good. And just like the top one, let's balance this out. You can actually put 2 here, and 2 times 3 is 6, right? And 2 times 2 is 6, and then you have 4 aluminum. Very good. Okay. And so just like that, we balance it, and I know that the charge of aluminum is 0, neutral. This is also 0. And we already defined the aluminum charges, which is +3, and oxygen is -2, right? So if I look at the aluminum, now aluminum actually gain electron or lose electron.
Aluminum gained electron.
Say it again.
Wait, actually,
Lose, right?
it lost.
Again, lose electron, lose electron. Everybody see that, right?
Mm.
Right? So it's lose or lost electron, let's say. And if you lost electron,
It's
it means
oxidized.
it's oxidation.
Mhm.
Professor, I have a question. On the left side of the equation, is every element going to be a neutral charge?
And not all the time, no. Again, depending on what you have, right? If you have a compound, then you might have actually charges. But in this case, it was neutral. But you cannot just generalize, oh, everything on the right or everything on the left is going to have this charge or that charge. No, that won't fly. Make sense?
Yeah.
Okay, so let's look at the oxygen now. And if you look at the oxygen now, oxygen is again going from 0. I don't have this space. I have to erase a little bit more. But you get the idea, right? So oxygen here, as you can see, it actually gain electrons, right? It gain electrons. Okay, so therefore, if you gain electron, it's a reduction, right?
Reduced.
Reduced. Yeah, let's say reduced, actually, that's a better word. Reduced. So oxygen is reduced and aluminum is oxidized, right? Oxidized. However, the question is asking oxidized. The question is the substance being oxidized. Yeah. So the substance being oxidized is what?
Aluminum.
Aluminum. And the substance being reduced is
Oxygen.
oxygen. But if I ask you which one will be the oxidizing agent,
Aluminum.
which one will be the oxidizing agent?
Oxygen.
Oxygen, right? Because oxygen is whatever, like if you're causing the other one to oxidize, then you are an oxidizing agent. Okay, you're kind of like, if you are being oxidized, you are the opposite, right? You are the reducing agent. Okay, if you are being reduced, if you are an oxygen, then you cause aluminum to oxidize. So therefore, I can call you an oxidizing agent. Make sense, right?
Mhm.
Okay, just don't mix those things. Sometimes you can mix it up, but I think it's clear. Okay, any question with this, everyone?
Ah, this is pretty good.
All right.
That was chapter 7.
All right. So before we move on to chapter 7, let's do one more about this. I'm just going to give you a balance. I'm just going to ask you to balance the rest reaction, okay? Yeah, let's say you have, this is actually, Carlos, this is the question that you ask, a little bit related, magnesium. Okay, so you have magnesium metal plus, plus nitrogen gas. And then you are producing magnesium nitrate. Magnesium nitrite. It's not nitrate, right? Nitrite.
Mhm. I got it now.
Okay, so let's write it down and then balance the equation.
Professor, if it would be nitrate, it would be Mg2 and 3, right?
Yeah. Again, it was, I think, yeah.
Mhm.
If it's a nitrate, this is different, guys. Nitrate. This will be NO3 with a negative charge minus.
Mhm.
back in the days, we have these paper quizzes. Now, everything is Canvas. All right. So what is the magnesium metal? What's the symbol?
Mg.
Mg,
Mg. Nitrogen gas.
N2.
Again, because nitrogen gas, it's a N, not N, it's a N2, right?
Same as
Okay.
oxygen, right? Can
Yep,
stand by.
same as oxygen. And all the halogens, right? If it's a halogen like fluorine, chlorine, bromine, iodine, or those are all diatomic, okay? And so what's the magnesium? Magnesium, let's write the formula. What's the charge?
+2 magnesium.
+2, right? And then nitrogen, what's the charge of nitrogen?
It's -3.
-3, right? And if you do the crisscrossing, you're gonna put this 3 here and 2 here. So you're gonna get magnesium 2, I mean, sorry, 3, right?
Magnesium 3,
Yep, and then nitrate
2.
2, okay? And so this is not so bad, right? We have 3 off here. If I put 3, that's gonna be already taken care of, right? So you have 2 nitrogen and 3 magnesium, okay?
So how do you balance it then?
It's balanced, see? I do the balance by putting 3 here.
Oh,
See?
oh, I see. I see.
Yeah, because I have 3 magnesium here, right?
Yeah.
And if I put 3 magnesium, yeah, magnesium is balanced and nitrogen is already balanced. I have 2 nitrogen and 2 nitrogen. I don't have to worry about it. Okay? Makes sense, right?
Yeah.
All right, cool. Again, just be careful about the some of the gases, like again, nitrogen gas, hydrogen. Oh, hydrogen is also always H2, right? Even though it's in group 1, it's a non-metal, and it's going to be exist as diatomic gas. Okay. All right. So I think we're done with this chapter, guys. Unless you have a question. All right. So that wasn't so bad. Again, I'm going to have a quiz on this chapter, and I'm going to move on to next chapter, but we are not going to finish the next chapter, okay? And since we didn't finish, we are not going to finish the next chapter, there won't be any quizzes for next chapter. So so the quiz is just going to be on chapter, what number? Chapter 7. All right. And let me just check my PowerPoint, see if yeah, mix it up. Yeah, this is like another example, KBR. It's just the same information. Okay. So don't save this. And so here in this chapter, now we are actually going into solution chemistry. Okay, first we're going to learn about solution chemistry, and we're going to learn about acid and bases, and then we're going to look at some biological application of this acid and bases. Because why we need to learn the solution chemistry? Because like whenever you want to react with, let's say, 2 chemicals, right? Let's say you have sodium chloride and reacting with something else, right? So if the compound is solid, right, you will never mix up 2 solids together to make a reactions, right? Why is that? Because if you mix 2 solids, right? Let's say this is one compound A, and you have compound B, and then you are mixing it up. If you mix those 2 solid, what kind of mixture you get? Do you think it's going to be homogeneous or heterogeneous mixture?
Heterogeneous.
Heterogeneous, right? So because it's going to be heterogeneous, right, then the reaction is not going to really go nicely, right? Because it's not a nice mixture. So in order to make a homogeneous mixture, right, remember the first chapter, you need to have a solutions. Remember we said that if you have a sodium chloride in water, that's a homogeneous mixture, right? Because whenever the substance dissolved in the solvent, We're going to learn about what the solvent is in a second. Then you're going to have a nice solution. It's going to be evenly distributed so that you can have a nice reaction. Okay, so that's why we need to learn about solution. And then when we have a solution, then we're going to have a different unity, right? We in the solids we have moles, but what about in solution, right? Are we going to have moles or molars or whatever? So that's what we're going to be learning about in this chapter. Okay, a lot of learning goes, as you can see. Okay, so the first thing first, we need to learn about the terminology. Again, a solution, we kind of like touch on that, is a homogeneous mixture of two or more substances, right? So right now I'm drinking, for instance, tea, right? Some sort of tea, and it's kind of like homogeneous, right? Because the tea is dissolved in water. And again, I give you this example, right? If I sip once, twice, or twice, like if I drink the whole thing, I'm going to have the same probably concentration throughout. Okay, so that's why it's going to be homogeneous. So whenever you have a solution, then you're going to have two things inside this solution, right? So this is like beaker, let's say. And so you have first a solute, right? Let's say you have sugar.
Mhm.
And if the sugar is dissolved in water, let's say this is water, blue.
It's gonna be solvent, right?
Yeah, right? So this is water. So you have like two things, right? One of them is the solute that you are dissolving, and the solvent is the liquid that you are using, right? Like whatever that solute is dissolved into, right? That's going to be the solvent. Make sense? Make sense?
It does.
So for example, if in a solution of salt water, right, the salt is the solute and water is the solvent. Make sense?
Mm.
Okay, makes sense, right?
Yeah, it does.
Okay. And I think I already give this example in the first or second chapter, right? Whenever you have two solutions, not all the solutions are going to mix together, right? Because if one of them is polar and one of them is non-polar, then they're not going to mix it up, okay? And in this case, if you have oil and vinegar, right, or oil and water, these are not going to mix it up.
Mhm.
And we call these two liquids or solutions, we call it immiscible. Immiscible means that they are not going to mix it up, right? They're not going to mix it up, they're going to separate it. And you can actually see a layer between them, and you can physically separate these two. And again, the solution rule is like, how come we can have a nice solution is the thumbs up rule is like dissolves like, meaning that if you have a polar substance, right, and the ionic substance are all polar, then you're gonna dissolve in the polar substance. And so if you have a non-polar substance, then it's gonna dissolve in non-polar. Like whenever you do like painting, for instance, right? The paint is if it's not a water-based paint, right? Then you cannot really clean the paint with water. What do you use? You use like ether, or some other chemical substance which is non-polar, so that it can dissolve, so that you can wash it out, right? So that you can clean. Again, the number one rule is again, and it works pretty much everywhere, like dissolves like. Okay.
Mhm.
Yeah, we kind of like talk about this. And then we have this, again, these are kind of like, again, some terminology, right? Whenever you have a solution, we have actually two type of solution, right? Either the solution is saturated. Saturated means that, let's say you are dissolving sodium chloride in 100 milliliter of water or a glass of water, okay? And you're adding 1 gram of salt, and then you dissolve, right? And then you add another gram, you dissolve, another gram, you dissolve, right? And at some point, right, the solution is gonna get saturated, right? And at that point, if you add sodium chloride in it, then it's not gonna dissolve, it's gonna stay on the bottom. And why is that? Because it's gonna be saturated, right? Because it has enough sodium chloride that dissolved in that solution, and every liquid is going to have a capacity, right? And we call this like solubility, okay? And again, we don't have to go dive into it, but you know, like, and it's giving like 10 gram per milliliter, or gram per milliliter, sorry. And at that point, then you won't be able to actually dissolve more solid into that solvent, basically. That's what it is. And again, unsaturated means it's still, you can still dissolve, right? You can still add more into it. That's what it is. And so when it comes to, again, solution, we're going to use actually two different units, okay? And the first one is percent by mass volume solutions. And this is actually used mostly in biological applications, right? You know, in chemistry, I mean, I don't like this unit, to be honest with you, and we never, like, in scientific papers, mostly if you are doing chemistry, right, we never report this, but in biological applications, right, if you are working in hospitals, they all use this percent by mass volume solutions. And what it is imagine you have a solution, right, and the solution is reported in volume, okay? And whenever you are reporting in volume, the unit that you are using is milliliters. That's the important part, okay? Milliliter. And then you are dividing how much solid that you have in grams, right? In grams. So basically, the percent by mass volume solution is mass over volume times 100, okay? That's what it is. And but again, the important thing here is you need to be the mass has to be in grams, right? And the volume has to be in milliliters. If I give you liters, you have to convert that into milliliters, okay? Because otherwise you're going to get wrong number. Let me give you an example. I'm going to come back to this modality. So let's do actual examples here. So I don't have any examples here. Let's go back to my whiteboard and let me see if I have any examples here. Hopefully I will. So let's say you have, let's do a quick example, 90 gram my 9 is kind of weird, huh? 90 gram of sodium chloride in 1.5 liter of solution. Okay, find the percent mass. Percent mass volume. And you will see actually sometimes this is actually abbreviated, right? Percent mass volume is abbreviated as MV. Okay. So let's find it. All right. What do we get, everyone?
6%.
Okay. So again, in order to get the mass volume percent, right, we need to actually find the mass of our solute right? And this has to be divided by the volume of solvent. So over here, the mass of solvent is obvious, right? They are giving 90 grams of sodium chloride. And which one is your solid? Is it sodium chloride or water? Which one is mass of solid here?
Sodium chloride is the
90
solute.
grams.
Right? 90, very good. So 90 grams, which is sodium chloride, divided by volume here. So here again, the trick is you cannot, you wouldn't want to be like putting 1.5 here. Otherwise, you're going to get a very high percentages, as you can see, right? This will be like more than 100%, right? So therefore, you need to actually convert this, right, the volume of solvent to milliliter. It has to be milliliter. So therefore, you're going to write down 1.5 liter is equal to, we know that, I don't know how many you do, you can do your conversion, but I guess you were taught like dimensional analysis most of the time, I guess, right? So you can say 1000 milliliter is equal to 1 liter, right? And if you do this math, liter is cancelled out.
It's
So
gonna
you're
be
going to get
1500, Professor.
1500. Say it again.
Yeah, I said it's gonna be 1500 milliliter.
1500, right?
Yeah.
Okay. So it's going to be 1500 milliliter. And then you just have to multiply this by times 100. Okay. And if you do this, what do you get? What's the answer? Boom, 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 boom. 9 times 10 is 10, 90. 9 divided by 15 is 6, I guess, right? So it's 6%. Makes sense, right? So this is telling you that, right? This is actually, if you have 100 milliliter of this solution, there's going to be always 6 grams in that 100 milliliter. And that's why it's going to be homogeneous. Make sense? So if I come and if I take 100 milliliter of the solutions, I will have 6 grams. If Carlos is going to come and take 100 milliliter, he's going to have 6 gram. If Timothy, Irene, or whoever comes in, if you take 100 milliliter, you're going to have exactly 6 gram of sodium chloride in that solution. Okay, that's what it means basically, 6%. Okay, any question with this? Clear, right? All right. So this is one way, and again, it's not the only way. And the other way is actually one that we like the most, the chemist. Okay, and in that case, we describe, right? We describe again. These are units for telling how much the solution is concentrated. Obviously, right? If I go back here, if I say 6% versus 20%, you can say the 20% is more concentrated. Makes sense because you have more solute in that solution. Makes sense, right? If it's 100%, it's like super, very saturated. So there's another way again. That way is we use molarity. And in that case, we describe the solution, how many moles of substance in 1 liter, in 1 liter, okay? And that's going to give you molarity. And then the symbol is M, capital M, and then you compare the M, right? Obviously, if you have 1 molar versus like 10 molar, right? The 10 molar is going to be more concentrated. Why? Because in per milliliter, you have more moles, right? Moles is, again, we learn about moles a little bit, not much, but we know what, at least what it means. It means you have more substance, more solute in that solution. That's why it's going to be more concentrated. And so let's actually do an exercise together. Let's do this together, and maybe next time you can do the I can give you another example maybe. So here, calculate the molarity of a solution that has 160 grams of NaOH, and then we are dissolving in this 6,000 milliliters. Okay, 6,000, yeah. So again, I know that let me just blow this up a little bit. right? We know we know how to find the molarity. It's moles over liters. So I need to find how many moles of sodium NaOH, sodium hydroxide, do I have, right? Because the volume is given, which is 6,000, but the moles is not given. They are just giving you the mass, right? So how can I actually get the moles out of the mass? We know, right? We know, I think I give you this, this formula. The moles is equal to what? Moles is equal to mass over molar mass, right? Right?
Yes.
And we know that the mass is given, which is 160 gram. So this is 160 gram of NaOH divided by the molar mass of NaOH. Molar mass is, again, remember, like when you were like going to periodic table and finding each element's atomic weight, and the atomic weight was like sodium is 23, oxygen is 16, hydrogen is 1, and if you add them up, you get 40 gram per mole, right? So if you divide this to this, you get 4 moles, right? It means that because we cannot measure the moles, we can measure the weight, but we cannot measure the moles. So that's why we always give the grams, right? And then you convert grams into the moles. So now you know that if you measure 160 gram of NaOH, sodium hydroxide, you have 4 moles of hydroxide. So now you can plug this in here, right? And all you have to do is here, before you do your math, is again, in molarity, we always use liters, okay? Not milliliters, not like in the percentages, always liters. So therefore, you have to do your conversion from 6,000 to 6 liters, and if you divide this, then you got your molarity, which is 0.67. Make sense?
Yes.
All right, very good. Okay, let's do one more example with this, and then we can move on. So now we are talking about molarity. Sodium chloride is, yeah, another good example, but yeah. What's the sodium chloride? Sodium is 23, 35, it's not an even number here. Okay, let's do this, another example. This is now, okay, what if you have 5 point, again, this is another example, 5.4 gram of HCl, hydrochloric acid. You measure this much, and you dissolve in this, right? You dissolve this in 500 milliliter of water. Okay, what's the molarity of solution? And hydrogen chloride is, I don't have myself, but yeah, this is 35.5, I believe, but you can check the chlorine. And hydrogen is 1, right? So it is around like 36.5, I guess. It's kind of like a lot of, not like, it's not an integer, so it's some decimal points, but I think you can handle it. All right. Okay, so let's do this together again. So again, in order to find the molarity, right, we need to find the moles of solute and the volume, right? And the moles is again moles, and the volumes has to be in liters, correct? Okay, so again, first thing first, I need to find the number of moles, because now they are just giving me the mass of this hydrogen chloride. So how can I find, again, right? We learned that the moles is equal to mass over molar mass, right? And the mass is given, which is 5.4 gram divided by, again, the molar mass is, again, you can just Google it, however you want to do it, right? You can just Google the molar mass of the hydrogen chloride. If not, if you have the periodic table in front of you, you can find the atomic weight of each element, and then you just add them up. And you can check, but did anybody check the atomic molar mass of the hydrogen chloride, right? It's 35.5 for hydrogen chlorine, right? If you have 1 mole of chlorine, it means that you have 35.5 gram, and then plus 1, it's going to add up to 36.5 gram per moles, right? Did anybody check this?
Yeah, that's right.
That's right? Okay, and again, if you do this, then the grams is going to cancel out, and then you're just going to have moles. And if you do this, what do you get, guys? Did anybody did this?
Like 0.15.
0.15,
Mhm.
right? Okay, good. You get 0.15 moles. Everybody's following, right?
Yeah.
If it doesn't make sense, I can again explain to you guys. If you have any questions, please don't hesitate, okay? Everybody. Joyce, Christina, Stephanie, Bianca,
Yeah,
We're good. I'm good.
Thomas.
I'm good.
Everybody's good? Yanyu?
Yes.
Okay.
But
Hopefully I'm saying your name right, but I'm terrible at spelling, guys, okay? Sometimes I mixed up my doser's name, so. All right, so we got this, right? And so we're gonna put this in moles. And finally, I know the volume, right? The volume is given, but I cannot just put 500 milliliter. Again, that's gonna be wrong. Because by definition, the molarity is how many moles of substance do you have in per liter. So therefore, you need to convert this. So how can I convert this to in liters? Then you're just gonna do your conversion factor, milliliters, times, you know that if you have 1 liter, it's gonna be 1000 milliliter, right?
Mhm.
And so again, we want to convert this into liters. So now milliliter is cancelled out. And as you can see, it is 5 divided by 10. So it's 0.5 liters, right?
Mhm.
So now you know this. So I can come back here and plug it in. And so if I do this, again, the unit is, it's kind of like a unitless number. I mean, moles per liter, moles divided by liter, but we're just like putting M. So if you do this, it's what, 0.03, I guess,
Yes.
right? And so it's going to be 0.03 mole.
0.3.
0.3? Oh, yeah, my math is wrong, I guess, yeah. Right? So it's going to be 0.3 M, right? 0.3 molars, basically. Okay? Make sense, everybody?
Good. Perfect.
All right, so let's move on. Again, those are two kind of like units that we use whenever we are describing the molarity. Okay, now I'm going to actually talk about acid and bases, and let's clear this mess up. Okay, And so let's write this acid here. Okay, and what are the acids? You probably heard about acids, right, all the time. What are the acids, guys? Anybody?
A pH.
pH?
pH from 1 to 6.
Yeah, 1 to 6, 1 to 7. But what's the definition though? Like, is water acid?
No,
No. Why? Why not?
water is neutral.
Okay. Why or why not? Okay. So again, but there are like, again, when it comes to acid, right? It was first defined by this guy whose name is Arrhenius, right? Arrhenius definition, and he noticed that actually some substance, right? If you have again substance, let's say you have an HA, okay, and he observed that actually some substance leave H pluses in aqueous solution. Aqueous means again water, right? So he actually described acid. You're an acid. If you dissolve in water, right?
Mhm.
You're gonna give up hydrogen plus. You're gonna give H pluses. We call this proton 2, and then you're gonna be an acid. Make sense?
Mhm.
For instance, look at sodium chloride. If I dissolve the sodium chloride in water, I get sodium pluses and chlorine minuses, right? And so by Arrhenius definition, I don't have any H pluses here. So therefore, sodium chloride is not an acid. Make sense? So that's actually the simplest and the first definition of Arrhenius acid. And it actually kind of like works for almost all the acids, but there are some exceptions. It doesn't really work. And therefore, we have other definitions like Lewis acid and bases, but we are not going to get into that. Okay, so we are fine with definition in these classes. Okay, so this is again, then this will be an acid. If I want to give you an example, for instance, like HCl, right? HCl is, again, if you dissolve, HCl is hydrogen chloride, and it's a gas actually, right? If you have a pure hydrogen chloride, it's a gas. But if you dissolve this gas into water, then it gives up H pluses in aqueous and then Cl minuses. And again, this is actually an acid.
Professor, I have a question.
Yeah.
Your, the acid it's gotta be the same metals to dissolve.
Say it again.
It has to be the same metals to dissolve.
What do you mean, like metals?
I mean, like it's gotta be the metals,
Metals?
or it could be metals and non-metals.
Oh, I see.
To
No,
dissolve
actually,
in water.
again, it doesn't really matter. It doesn't matter. Okay, but
Mhm.
but you have a point. Usually, the metals is gonna actually have bases. Okay,
Mhm.
we're gonna come to that. Okay,
Oh, okay.
but usually, yeah, if you have like we're gonna, yeah, I'm gonna come to that. Okay.
Okay, all right, thank you.
So if I want to give you another example, for instance, we talk about this, right? This is actually acetic acid, CH3COO minus. And this is gonna again give up H pluses. Okay, but now again, some reactions, right? In as you can see in these reactions, I put double arrow. In this reaction, I just put one arrow. In this reaction, I put double arrow. Again, this will actually depends on how strong acid is. Okay, if the acid is strong, it means that you're going to have a lot of H pluses in solution, right? And therefore, the reaction is going to move forward to one direction. But if the acid is weak, such as acetic acid, and acetic acid is weak because we can eat it, right? If it will be a strong acid, we wouldn't be like eating it. It will destroy us, right? And so therefore, the reaction is again, because acetic acid is weak, so it's not as strong as a hydrogen chloride, because you cannot really touch hydrogen chloride. If it's a very concentrated one, right, it will burn your skin. And if you stay longer, it will start eating up your skin, believe it or not, right? So, but acetic acid is not that strong because the reaction is not going forward like this way, right? It's actually going backward as well. We're going to come back to that later. But yeah, so this is again what the acid is. And the other thing that I want to mention here is, even though we say H pluses, it's actually, there is no such molecule, okay? If you have H pluses in water, H pluses is going to always react with water, and it's going to give us H3O plus. This is the real molecule, okay? There is no such H pluses, okay? You will never isolate it, but people actually isolated H3 pluses, and we have the crystal structure and everything. So whenever I say H pluses, it's really H3O pluses. It's hydronium ion, but it's the same thing basically. Make sense? Okay. And if you have an acid, right, we know it has a sour taste, because we know, like, if you drink like Coke, if you drink like lemon, right, it's all sour taste. And it will actually, again, change the litmus paper. If you have a blue litmus paper, right, if you have a blue litmus paper, like, how can you know if the solution is acidic? If you have a litmus paper, you dip it in the blue litmus paper. If the blue turns red, then it means it's an acid, okay? And then we're gonna talk about pH scale in a little bit, but this is like another example. And also, it can react with metals. Again, we just talked about this, right? Remember the single replacement reaction? It can do a single replacement reaction with the metals, and it can neutralize bases, okay? So again, these are the properties of the acids. And what about the base? The bases, on the other hand, let's write the bases here, in the blue. So bases, on the other hand, it is, again, the Arrhenius definition of the bases here is that any substance, let's take a look at NaOH, that will release, instead of releasing H pluses or hydronium ion, now we are actually releasing OH. What was the OH minus name? Remember the polyatomic name?
Hydroxyl.
Hydroxide. Very good. Right. Again, this is again hydroxide. Maybe I can zoom out a little bit. Yeah. You can see it, right? Again, this is hydroxide. So if a substance or a chemical releases OH minuses in aqueous solution, then you are a base. This is the definition of Arrhenius, okay? And again, back to Irene's questions, usually if the metals, right, like sodium is metal, like if you are a barium or magnesium or potassium, right, these are gonna be actually, whenever they react with the hydroxide, they're gonna actually produce a basis. And that's why, usually, metals are gonna be actually producing bases. And again, sodium hydroxide is another base, right? And I can give you, and this is a strong base, magnesium hydroxide is a base, etc. And it's the kind of like the opposite of the acid, right? So how can you say whether you have a base or not, right? Then if you have a red litmus paper, and if you dip it in a basic solution, if it's really basic, then it will turn into blue, right? So acid is turning blue to red, but base is turning red to blue, okay? And if you look at the properties of the base, it is actually, anybody knows the taste of the base? What kind of taste? I'm sure you didn't taste it, but does anybody remember that whenever you're like taking a shower, you probably, like when you were a kid, you kind of like, you get like soap in your mouth.
Is it bitter?
Yeah, right. It's a bitter again because when you have a soap, I think we're going to talk about in organic chemistry, right? The soaps are made of the bases, right? They have you have like this big fatty acids, and the fatty acid is reacting with the sodium hydroxide, and then you have some hydroxide left over, and that's why it's kind of like giving you that bitter taste. And the other thing is also, if you have a hydroxide in the solution, it's kind of like it's gonna give you a slippery feeling. Okay, it's gonna like when you touch your hands, and it's gonna be very slippy. And the other thing is like, you know, if you drink like some water, like some spring water, like if you go to like Poconos, I don't know, or in other mountains, and some of the spring waters are really alkaline, right? So alkaline means that they have some alkali metals, and it makes them basic, and they have hydroxide ion inside, and that's why it's gonna give you like those slippery feeling. Like I remember when I was a kid, I was like washing my hands with water, and I thought that it's like it gets never clean because it's like so slippery, you know, because the water is basic. Okay, and those waters are good actually. I mean, okay, so those are going to be our bases. And again, it can actually, they can react with the acids so that we can actually neutralize. And again, whenever you have an acid and base, right, then it will react with themselves, right? Oops, where am I? So if you have an acid such as HCl, and then if you bring this with NOH, you can actually define almost all the reactions, believe it or not, almost all, but most of the reactions is acid-base reactions, by the way, guys. Because if you have acid and a base, there will be a violent reaction between them, right? They like each other. And it's kind of like a double replacement too, in a way, right? So you're replacing this cation and an ion with this. And so whenever you have acid and base, you're going to always have salt, right? So the salt is going to be, again, sodium chloride here in this case. And you're going to always have water. Okay. You see, you're kind of like replacing this with this, right? With this H. Sorry. Kind of like a double replacement reaction. And the chlorine and the hydrogen comes here so that you can get water. Okay, so again, they will react very violently and they like each other. Again, there are some other examples like sodium hydroxide, calcium hydroxide is another example, right? This is metal 2, this is metal 2, and they are all base, and they will react with acids. And then again, I briefly talk about the strength of the acid and bases, and what determines how the acid is strength is its ability to give up that H pluses, right? So again, these are the strong acid and bases. If you look at the HCl, sulfuric acid, nitric acid, sodium hydroxide, potassium hydroxide, these are very strong acid and bases. Why? Because they are very actually they don't mind giving up the H pluses, right, to the aqueous solution. That's why they are strong. However, I think I have the weak acid too. If you look at the acetic acid again, for instance, right, acetic acid is not really happy. I can give you, I can go back to my table again. Yeah. Again, if you're going to come to my organic chemistry classes, we will talk about this in more detail, but in short, all right, we talk about two things here: ionization first, and the second thing is how the conjugated base is stable. Basically, if I compare these two, right, what makes them HCl a strong acid is because HCl is is ionizable 100%, and meaning that it will, if you have like 1 molar of HCl, right? And if you dissolve this 1 molar in water, you will get 1 molar of H pluses and 1 molar of Cl minuses, right? Okay. However, if you have 1 molar of acetic acid, right, it will not ionize 100%. And in fact, I think I have it here somewhere. See, only 0.4% ionizes, meaning that 1 molar times 0.4%, like this much you're gonna get, right? So you're gonna get really like a tiny amount, really. Makes sense? It's gonna be like what? It's gonna be like 0.04 molar. You see the difference, right? And what was the definition of the acid? The definition of the acid is the ability to give H pluses, right? The proton in aqueous solution. And as you compare this, now you have 1 molar of H pluses versus 0.04 molar. Which one is larger? 1 molar, right? It's actually 96 times larger, right? Like there's a huge difference. And that's why the HCl is going to be strong acid, right? This is going to be strong acid. And this will be a weak acid. Make sense? And you might be asking, like, what makes this weak, or again, this is like an organic chemistry topic, but because acetic acid is not happy without that hydrogen. Make sense? Like whenever you give up the H pluses, like imagine you have, I know this is not a good example, but imagine you have, you know, like girlfriend or boyfriend, or you're married, right? You are like doing a separation, right? So how can you separate, right? If you are happy without her or him, right, you can just easily separate, right? You can just say bye-bye, I'm really happy, you know, just like that, acetic acid. But if you are not happy, right, then the separation is going to take years because you don't want to like separate, like don't leave me, right? So acetic acid is like that. It doesn't like to give that H pluses easily because it's not happy without H pluses. However, the HCl, hydrogen chloric acid, is happy, right? So it's saying, okay, just take away, like go, right? So that's why the HCl, hydrogen chloride, is going to be pretty strong acid. However, acetic acid is not going to be strong. Hopefully it makes sense, right?
Yeah, it
Again,
does.
you don't have to worry about this too much. I'm not going to be like asking, compare the acidity of these acids. That's more like organic chemistry talk, okay? But so you know, like where the strength of the acidity and basicity comes from. Again, these are some weak acids and base. And now we can actually come to the pH scale, right? And if I go back to my table again, right? So how can we then compare the acidity and basicity of these solutions? Like how strong is it? Like because we want to have like quantify, right? We don't want to be like saying, oh, qualitatively this is acidic, basic, but how acidic is it? How basic is it? And in that case, we use the pH scale. And let me give you, yeah, maybe I can just show you here. So we use actually from 0, right? Let's say this is 7. And from here, we use another one. Let's say this is base, right? So we use this pH scale and it goes from 0 to 14, right? Everybody's awake, right? Nobody's sleeping.
No, we're here.
Do
We're
you guys need a break or something?
No,
Everybody's good?
Yeah.
So it's kind of like a, I don't see you guys, but yeah, I see thumbs up. Okay, I'm not gonna keep you long, okay? I'm gonna let you another 30 minutes or so maybe, and then I'm gonna let you guys go, okay?
Okay.
but I'm not going to finish this whole chapter because this is like kind of like a long chapter. All right, so this is actually, again, we use this pH scale, and if the pH, and I'm going to talk about this pH in a second, it's between 0 to 7, then you're acidic, okay? If the pH is between 7 to 14, then you are basic, okay? So how can I find the pH then, right? So the pH is, again, defined as, right, we talk about the concentration of the hydronium ion, correct? And the H plus ion. So the H plus ion is, even though we have 1 molar here, right? Sometimes we're gonna get like very absurd numbers, like again, like 0.04 molar, for instance, right? So instead of like getting like all like decimal points, right? You wanna get rid of those, and that's why we apply this negative log. This is a mathematical operation of the H plus concentration. Make sense? Whenever you apply the natural log of the hydronium ion concentration, then you're going to find the pH. And again, that is how we are defining the pH. Make sense?
Yes.
I'm going to show you some examples, guys. Don't worry about it. And usually we are going to be actually giving you, right? You can either use your calculator, but in this class, I'm not going to be like asking like very like 2 or 3 significant figures, maybe 4. We're just going to use 10 to the negative power, either, and this is going to be like integer. And I'm going to just show you how can you do that without using the calculator. So let's say the hydronium ion concentration is, right, let's say you have the H plus concentration is very small, 10 to the negative 7 molar. And I'm going to find out the pH of this solution. So all you have to do is, again, just plug this number in here, right? And let's do that. And if you have a negative log of 10 to the negative 7, okay, in mathematics, again, I'm not a mathematics professor, but whenever you have log 10, right, and these are going to actually cancel out each other, and this number is going to come in front of the log. So therefore, you're going to have negative here, right? There's a negative here, and there's another negative 7. And if you multiply these two, you're going to get 7. Okay, if you don't believe me, you can do it with your calculator. Okay, that's fine. But in this class, we're going to always use this kind of concentration, guys. Okay, I'm not going to give you like 3.5 times 10 to negative 7. Okay, you cannot apply to that. But as long as you have a base 10, right, then you can apply this. Make sense? So again, this is the pH, and we will do some examples, by the way. And let me see. Okay, these are pH. Okay, we talk about salts right away. We can stop salts, and then let's talk about, okay, so if this is the pH, then what about the pOH, right? Because now, whenever I talk about the pH means how much hydrogen do you have? And at the same time, you can use also pOH. And pOH is telling you the hydroxide concentration, right? And so what is the definition of pH and pOH? I can give you this definition, right? If you add them up, it's going to be always 14, okay? pH plus pOH is going to be always 14. So if the pH is 7, then pOH is going to be also 7. Okay? Everybody make sense? Or you may be asking like, where, again, I'm not going to show you where this is like driving, because you don't have to worry about it. This is actually driving from whenever you have a hydrogen concentration times the OH concentration, it's going to be always 10 to the negative 14, okay? And whenever you get the log of these sides, both sides, that's where this this pH plus pOH is 14. Okay, that's where it's deriving from, but you don't have to worry about how we are driving these formulas. Okay, so meaning that if you have one of them, then you can find the other basically, and that's exactly how the question is going to be coming, right? If I'm going to be giving you the pH of a solution which is 2, I'm going to ask you to find the pOH, for instance, as such. Any question with this, guys? Nobody's falling?
Yeah.
Nobody's sleeping, right? I'm not asking you to turn on your cameras, but hopefully you're not in the bed.
No.
No, we're here.
You can be in the bed, but at least your eyes is as long as your eyes is open. Okay, let's do an example, and I'm gonna keep you here so that you can actually look at this definition. Yeah. So let's say I'm gonna give you a table. And so this is the H plus concentration. And this is the OH concentration. And I'm going to ask you to find the pH of the solution. And I'm going to ask you to find whether it's acidic or basic. And I'm going to give you one example here, which is 10 to the negative 5 molar. Okay, this is number 1. Let's do 1 and 2. I think 2 will be enough, I guess. And then let's say I'm going to give you the pH of a solution, which is 2. And you're going to fill in the blanks, okay? And let's do one more. Let's say this is 10 to the negative 7. So let's fill out this table basically. All right. Okay, let's look at the first one together, and then maybe you can do the second and third. So if the hydrogen ion concentration, H plus concentration is 10 to the negative 5 molar again, right? So the unit is molar, but I don't have to write it because we usually give the H pluses. Whenever you see this bracket, right, 2 bracket, it means that's the concentration, okay? I think I forgot to tell you that, but that's actually how you use the concentration in chemistry. So if it's 10 to the negative 5, can I find the pH of this solution? I can, right? Because pH is equal to negative log of hydrogen ion concentration, correct? So again, just like the way that I did here, if I plug this number in, negative log of hydrogen concentration is what? 10 to the 5, negative 5. So what's the pH here?
5.
5, right? Very good. Okay, so pH is 5, all right? And if the pH is 5, I know that it's smaller than 7, so this must be acidic. But what about the OHs? How can I find the OHs? Did anybody find the OH?
10 to the negative 9.
Negative 9. How did you find it, Timothy?
It has to add up to 14.
14. Okay, again, you can do this like two ways, right? Again, I gave you this formula, or you can use this one, like either way, right? So let's use the first one, I mean the second one, this one, right? So if one of them is, I know the one of them is 10 to the negative 5, so I know that 10 to the negative 5 times OH concentration is going to be 10 to negative 14, right? So now I can find the OH concentration, right? Because if I divide everywhere 10 to the negative 5, again, this is a little bit math involved, but I think it's not so bad. So now I can cancel this out and I can find the OH concentration, right? What's the OH concentration then? Again, if you have, you need to know a little bit of math, right? If you have the same base, you can subtract whenever you have a division like that. So 10, negative 14, minus 5. So it's going to be equal to 10, negative 9, right? Everybody's following, right?
Yes.
Okay. And now if I'm asking the POH, again, POH is definition, is the same thing, right? You're going to get the negative log of the OH concentration, same thing. And if you do the math, again, it's 10 to the negative 9. So if you do the math, 10 to the negative 9, right? So you're going to get 9. Because also, you know, as Timothy was saying that this has to be add up to 14. As you can see, pH plus POH is 9. But here, they are just asking the OH concentration, actually. Yeah, I kind of like jump off. So the OH concentration I already defined here. You see that, right? 10 to the negative 9. If I ask you the POH will be what? 9, right?
Mm-hmm.
Okay, everybody's following, right? Everybody's good? Irene, Marcos,
Yes, good.
I think
Garcia, Jessica, Stephanie,
Yes.
Good.
Christina,
Good.
Joyce.
Good, thank you.
All right, so let's fill up the second one then. Now I'm asking you the pH, and I'm going to ask you to find the hydronium ion concentration and OH concentration.
the hydrogen concentration would be 10 to negative 2, and the OH concentration would be 10 to negative 12,
Okay, sounds about right.
and it's acid.
Okay, so again, if the pH is 2, right? If the pH is 2, I'm looking this one, guys. So again, pH is 2 is equal to negative log of H pluses, right? You can again do this either with your calculator, but you know, if this is 2, it means that this is 10 to the negative 2, right?
Yep.
This is what we learned, right? The hydronium ion concentration has to be 10 to the negative 2 power. Okay, so I can plug this in here, 10 to the negative 2. And if this is negative 2, then it has to be add up to negative 14 right here, as we just did it for the first one, right? So therefore, negative 2 plus negative 12 is going to add up to negative 14. Make sense?
Yep.
Okay, and this has to be also acidic, right? Let's write acidic red.
And POH would be 12.
Okay, and the POH, it will be 12, right? If you get to the negative log, it will be 12. Very good. Okay. Okay, what about the last one?
OH 10 to negative 7, pH 7, and neutral, or
Okay, so again here it is negative 7. So I know that if you multiply these two, it has to be add up to negative 14. So therefore, this must be negative 7, right? Because if you basically, yeah, right, if you add this up, it has to add up to negative 14 or 14, right?
right.
Make sense? Negative 14, sorry, not 14. Okay, so therefore, if this is negative 10, negative 7, the OH concentration is going to be negative 7, and the pH is going to be the natural log of the negative log of the 10 to the negative 7. So therefore, it's going to be 7, and this is going to be again neutral, right? Because it's right in the middle. Hopefully, it makes sense, right, everybody?
Yeah.
Okay. So, any question with this, everyone?
No, Professor.
Everybody's good?
Mm-hmm.
Okay, I'm going to ask you one more question before I let you guys go. Okay, so this is, let's say this is the first solution, right? So if I ask you, right, how much acidic, like how much acidic the second solution is, like if I compare the first one and second one, right? If I ask you which one is going to be more acidic,
The second one,
second one, why?
because it's the one is the most acidic on the pH scale, and 6 is the least. 7 is neutral, and then 8 is the least base, and then 14 is the highest base.
Right? So if the pH is lower, it means it's more stronger, okay? Right?
Yep.
Yeah.
Okay, so the 2 is the, again, I'm just comparing 1 and 2 right now. And so I know that 2 is more acidic, but how much more acidic? Like how many times more acidic?
It's 3 pH more acidic.
How many times?
So
Or how many
So-
times stronger?
1,000 times, right?
How many times stronger?
12,000. 12,000.
Huh?
12,000.
1,000?
Yeah, each
Oops.
pH number is 10, right? It's like it's exponential.
Yes, right? Again, here, if you have a question, it's asking you how many times, like how much stronger is it, right? You're not just gonna divide the pH up. You're not just gonna say, oh, okay, it's 5 divided by 2, it's like twice. No, that will be wrong, because as I think Thomas, he was saying, it's gonna be the 10 power. So what you have to do here is you have to divide this up, right? You have to divide the hydronium concentration up. Make sense? So it's gonna be the second one is, right? If you look at the second one, what's the hydronium concentration? 10 to the negative 2, right? Divided by, what's the first one? 10 to the negative 5, right? And if you divide this up, again, the same rule applies, right? If the base is the same, we can do a subtraction on the, what you call this? Exponents, I guess, right? And so you're gonna get, again, 10 to the third power, right? So it's, again, the second solution is 1,000 times stronger, basically, and 1,000 times more acidic than the first one. Make sense?
Yeah.
Again, if you're comparing acidity and basicity, the pH is giving you a sense, but in actual number, right, it's going to be 1,000 times more stronger than the first solution. And again, you can compare the second one, the third one, and etc. Right? As you can see, if you change the pH 1 scale, you're actually making 10 times stronger or 10 times, weaker. Okay. All right, guys. I think I'm gonna stop here. I'm also tired, by the way. It's been like almost 2 hours, right? It is pretty good, actually. Yeah, let's stop here. I'm gonna stop in the salts and let's stop sharing and let's stop recording.